UCSD ECE 111 Lecture 3, Field Programmable Gate Arrays or FPGAs. Lecture 3 Set 1, Memory Arrays. We have, when you think about computing and hardware, there are different choices. Here I'm putting 3 popular choices for computing. One is general purpose processing. The other one is application-specific integrated circuit, or in short, ASIC. And in the middle, somewhere in the middle, is reconfigurable logic, as you see here. There are pros and cons for these different computing systems. For example, if we choose a general purpose processor, the cool thing is a lot more people know how to program in software, so we get a lot of flexibility, a lot of scalability from the system, but this is not exactly the best performance we could get from a hardware system. At the end of this spectrum is application-specific IC or ASIC, where we get very fast, very good performance, very low power performance, but this is very inflexible. And there is a cost also associated with it. When we design a general purpose processor, it's a one-time design that we pay, and then we could run many software programs on the top. But if we design an application-specific chip, it will be really great performance, but it will not be flexible. We cannot really do other functions on the top of an ASIC chip, and that actually limits the cost that that we pay upfront for it. When we design an application-specific chip, what happens typically is that we are going to send we're going to go through the Verilog synthesis, as we will show later in the slide set, but we also going to generate a file that goes to the foundry for generating a mask, and making a mask is a super expensive process. What happens is that we have to the company that is trying to design this has to pay a lot of upfront costs for making the mask, and then once you have the mask, then making chips out of that mask is reasonably cheap in the order of cents. So if a company has a high volume of production, then its economy of scale makes sense to go through the costs of making an ASIC chip, but also at the if this is used many times, then it's worth really going down and making that inflexible platform that is highly optimized. But if you are looking in the middle, the middle ground here is reconfigurable computer, where the performance is way better than a general purpose processor. We get a fair amount of hardware parallelism from a piece of hardware, as opposed to general purpose processor, where we have to wait for the instructions to go one by one to each thread. But we also get some degree of programmability into the hardware. You guys have all heard about the big data realm. One thing that is the common denominator for a big data realm is the fact that we have to store large amounts of data. So in this context, no matter which computing platform you use, the memory arrays are going to be a really important part of the computing system. And the memory arrays, which are basically arrays or matrices of memory, they are the arrays that there are the structures that efficiently store large amounts of data. There is no one option available in terms of memory. There are different technologies available, and unfortunately, not any of them has the best in all different aspects. Some of them have a higher integration. There are smaller, but not as good performance, and maybe the power performance is also important as well as the timing performance. And there are for this very reason, the memory inside any of these processors is typically not just one piece. It's typically a hybrid of various different memory options that we have in each of these processors, and then when the architecture is done, it is such that for every task we are going to use the appropriate type of memory that gives us the best performance for that task. For example, you guys may all be familiar with the notion of a memory of a processor versus the cache. The cache is typically smaller, but it's faster. So for work that is done very and needs fast performance, and for values that we are storing locally when we run the programs, we use the cache, and there are different levels of the cache. Each of the levels has its own certain limit, in addition to the performance, and that's how we optimize the different programs, or the compilers optimize the different programs in a general purpose processor. In typical options for memory include the dynamic random access memory, or in short, DRAM. Static random access memory, or in short, SRAM, and the read-only memory. These, as I mentioned earlier, these have trade-off with respect to the size and speed and so on and so forth, and the power they spend. The read-only memory is something that is also could be a nominal. In old times, we had memories that you could only read from, so they programmed those in the factory and then you could read from it. But in modern times, read-only memory is also used to indicate the memories that have asymmetric read and write, like very asymmetric read and write performance. It's typically much more costly to write to them. It's just like much more timely to read from them, as opposed to, it takes a much larger time to write to them, or much larger power to write to them. No matter what kind of memory you use, we typically have n bits to address the 2 to the power n locations in the memory, and then there are, every time you go to one of those addresses, typically the word length of the memory is this m bit that we're reading from. So this is typically the address, and this is the data coming out of the memory.